Physics doesn't care about your paperwork. Theoretical models like RANs often miss the reality of transient eddies, which create microenvironments that shield pathogens and compromise your sterilization processes, often at a massive financial cost. When you lose millions in hours, the problem isn't just the math. It's the gap between your ideal models and the high shear coalescing reality inside the tank. Those theoretical assumptions rarely hold up under physical stress. Inside the cellular arena, the mechanics are unforgiving. From impellers spinning at high speeds to the delicate balance of oxygen delivery for billions of cells, every variable, from circulation time to bubble breakup, is a critical factor in performance. The evolution of bioreactors shows a clear trend, but every solution brings new failure modes. As we move from static vessels to AI-optimized systems, our ability to predict these issues must evolve, or we risk falling into old traps. PINNs are a necessary fiction. They represent the map, not the physical territory. Real-world delays in sensors and flow logic often mean your system isn't operating where you think it is, leading to unexpected local conditions. Even small structural issues, like weld beads or impeller misalignment, can create major operational hurdles. These physical defects disrupt flow and harbor contaminants, turning theoretical efficiency into a maintenance nightmare. The governing equations, Navier-Stokes, Fick's law, and Monod kinetics, are the rules of the game. However, because real-world variables like viscosity and cellular lag differ from these assumptions, the field is often riddled with hidden challenges. There is a massive computational chasm between traditional CFD and modern AI surrogates. While PINNs offer incredible speed, remember the warning: an AI model can confidently hallucinate outside its training envelope. A cyber-physical collision occurs when a digital twin is fed perfect data from a flawed, fouled sensor environment. The result is a system making optimal decisions based on false premises, leading to costly disasters. If your reward function isn't aligned with physical reality, your controller might find a dangerous loophole. Optimizing for metrics without considering consequences can turn a standard controller into a system that sacrifices batch integrity. The gap between as-designed and as-built tolerances is where entropy thrives. From surface roughness to bolt torque, human variation is inevitable, and only obsessive vigilance can maintain the precision your process requires. Failure forensically reveals itself in layers. By the time mechanical symptoms are visible, the invisible biological shifts have already set the stage for disaster. Monitoring secondary diagnostics is essential to catch these issues early. AI provides the visionary design, but it requires a human realist to manage the manufacturing reality. Biomimetic impellers can improve performance significantly, but they demand precise post-processing to be effective. The future of bioengineering spans from current stirred tanks to planetary-scale bioreactors and beyond. As we merge biology and technology, the question becomes how we manage increasingly complex systems on a global scale. Ultimately, you cannot defeat entropy, but with rigorous engineering and AI as your co-pilot, you can manage it. Focus on building systems that provide real value, reduce wait times, and save lives.